The next thing we're going to look at in section 3.2 is rates of change. A common use for rate of change is to describe the motion of an object that moves in a straight line. In such problems, it is customary to either use a horizontal or vertical line with a designed origin to represent the line of motion. On such lines, movement right is considered upward in the positive direction, or if we're going left or downward, that would be considered to be the negative direction. We're going to look at a position function. Let's suppose we can state on a vertical line our position at time t will be given by the function s of t. So s is going to be our position function. If we think about like classical rates, if you wanted to know kind of like the average rate of change or the average speed of something between two time periods, it's simply going to be the change in the distance. That's the change in the position. That's going to be delta s divided by the change in time. That's going to be delta t. Okay. In example 10, let's suppose that we have a billiard ball is dropped from a height of 100 feet, and the equation that's going to model the position of the ball in terms of its height is going to be given by s equals negative 16t squared plus 100, where s is measured in feet and t is measured in seconds. Let's find the average velocity over each of the following subintervals. Okay, so if you want to, it's not a bad idea, but let's think about kind of the vertical motion of this ball. So this ball is being dropped, so it's going to be modeled kind of by like a vertical line, but it's going to have linear motion along a straight line. We know that we start at 100 feet, and you could check this that at s of 0, we're starting at 100 feet. And then if you want to know, okay, well, what is the height or what is the position above the ground at any time, you tell us what time you want. That's the value t in seconds. And then this will give us the position or the height of the ball would be given by the function s of t. Okay. The first thing we want to do is find the average velocity over the interval 1 to 2. That's going to be the change in the distance divided by the change in the time, which can also be thought of as the final position minus the initial position divided by the final time minus the initial time. So if we're looking at, let's say, the average rate of change of a function in general, doesn't even have to necessarily be a position function, over the closed interval a to b, the average value, the average rate of change I should say, so I'm just going to abbreviate it, ROC, is found by doing f of b minus f of a divided by b minus a. So for us, this would be s of 2 minus s of 1 divided by 2 minus 1, where these two terms in the numerator are actually function evaluations. I'll show the first one if I plug 2 into this function. Recall s of t is negative 16t squared plus 100. If I evaluate s of 2, that's going to be negative 16 times 2 squared plus 100, which will be negative 64 plus 100, which will be positive 36. So the position of the projectile at time, it's a billiard ball I guess, so the position of the billiard ball at 2 seconds would be 36 feet above the ground. Similarly, you could plug s of 1 in, it's going to be 84 feet, divided by 2 minus 1, which is 1, and we would get that the average rate of change of the speed of the ball in that interval would be negative 48 feet per second. Let's do this on a slightly different interval. Let's do it on the interval 1 to 1.5. What would be the average rate of change over this interval? Well, this would be s of 1.5 minus s of 1 divided by 1.5 minus 1. The good news is s of 1, we already did that part from the previous calculation. You'd want to plug 1.5 into the function. If you did s of 1.5, I'm not going to work it out, but this is what calculators are great at. It would be negative 16 times 1.5 squared plus 100. You should find that that value would be 64. So it's going to be 64 minus 84 divided by 0.5, which is going to be equal to negative 20 divided by 0.5, which is going to be negative 40 feet per second. And now we'll do one more of these, which is going to be the average rate of change over the interval 1 to 1.1. So at each point, if you look at the sequence here we're kind of going through, and going from problems A through C, we're looking at each point in time an interval that begins at 1. And then we're looking at a second time, which is getting successively closer to our first time of 1. So we started from 1 to 2. Now we're going to look at from 1 to 1.5. Now we're looking at 1 to 1.1. So we're really kind of thinking of this as kind of like the interval 1, 2, 1 plus delta t, where the delta t is getting smaller. In the first one, we had to add 1 to get to the interval of 2. In this one, we had to add a half. Now we're only adding 0.1 to get to the second point in our interval. If you calculate this average rate of change, s of 1.1 divided by s of 1 divided by 1.1 minus 1, that would produce negative 33.6 feet. And so what's happening here is we're starting to kind of investigate. If you look at the series of outputs, it went from negative 48 feet per second to negative 40 to negative 33.6. What we're beginning to do is to approximate the instantaneous velocity, which would be the question of asking what is the velocity at the instance t equals to 1. So at t equals to 1 second, what is the velocity of the billiard ball? And we know that the instantaneous velocity is given by the derivative. And in this case, we know that s prime of t is equal to the limit as delta t approaches to 0. We can write it as s of t plus delta t minus s of t all divided by delta t. And if we kind of use our derivative rules from earlier in this section, this is just a polynomial, we would know that s prime of t, so think of the t almost like an x variable, the derivative of this is going to be simply negative 32t, and therefore the instantaneous velocity, the s prime of 1, everywhere I see a t, I would plug in 1, which would give us negative 32 feet per second, which would be the instantaneous velocity of the billiard ball at time equals to 1 second. So you can see that we're kind of approximating it here by letting delta t go to 0. And what we see is that the outputs we're getting successively closer to negative 32, which would have been the limit in this case. So if we're talking about an average rate of change, just be aware that this would be the average rate of change over the interval a to b. But the moment we begin to talk about instantaneous rate of change or instantaneous velocity, that's going to be the derivative. Okay. And this leads us into the next part of it. In general, if s equals to s of t is the position function for an object moving along a straight line, then the velocity of the object is simply going to be the derivative of its position. The speed of an object is the absolute value of its velocity. So very, very important here. Kind of something very important to talk about and to consider right now. So one of the things we all might kind of remember from physics is that things like speed and velocity, these are what we call vector quantities. Okay? And what's important about a vector quantity is it's something that has both a magnitude and direction. In this context, when we talk about one-dimensional motion, okay, the magnitude is kind of the absolute value of the value that we get out. And then whether the value is positive or negative, that's what's indicating to us the direction. Remember, positive could mean either going up or going to the right, depending upon whether you're looking at horizontal or vertical motion. And then a negative direction would be either going down for vertical motion or to the left for horizontal motion. So don't confuse velocity with speed. Velocity itself is a vector quantity. It has both magnitude and direction. If somebody's only concerned with, relatively speaking, how fast is something traveling, in other words, what is the speed? Speed is the absolute value of velocity. Speed does not concern itself with which direction it's moving. It just wants to know what is the magnitude of the instantaneous rate of change. Okay, so speed for us is the absolute value of velocity. A common application we'll kind of look at will be free fall or projectile motion under the assumption that we neglect air resistance. So if we look at, let's suppose you throw something on a plane that has a gravity of g, and you throw it with initial velocity component in the direction of motion v sub 0 from an initial position of s sub 0. Then the position function for that object would be given by s of t equals 1/2 gt squared plus v sub 0t plus s sub 0. We will actually derive this equation towards the end of the class when we get to our section on integration. But in particular, if we're looking at projectile motion, let's say on Earth, if you're using English units, it would be negative 32 feet per second for us would be g, or in the metric system, it would be negative 9.8 meters per second for g. Let's take a look at an example in number 11. It says, at time equal to 0, a diver jumps from a platform diving board that is 32 feet above the water. Because the initial velocity of the diver is 16 feet per second, the position function of the diver would be given by the following function. S of t equals negative 16t squared plus 16t plus 32, where t is time in seconds, and s of t would be the distance above the water. The first question asks, when does the diver hit the water? So whenever they hit the water, that's going to correspond to whenever the height would be equal to 0. So to solve this, we need to set the position function equal to 0 and solve. So we want to know when is negative 16t squared plus 16t plus 32 equals to 0. This is a quadratic equation. Furthermore, we can reduce all of these coefficients before doing anything else because every single term is divisible by 16. But in particular, because the leading coefficient is negative, I would prefer for it to be positive. So we can kind of divide everything by a negative 16. This gives us the much simpler and equivalent t squared minus t minus 2 to solve. This factors as t minus 2 times t plus 1 equals to 0. We can set each factor equal to 0 individually. T minus 2 equals to 0, t plus 1 equals to 0, and we would get two solutions. One would be t equals to 2 seconds. The other would be t equals to negative 1 second. Okay. For an application problem like this function, s of t, only models the height of the diver after they jump. So it's only valid for time greater than or equal to 0, which means the only solution that would make sense here would be t equals to 2 seconds. Furthermore, because this is a application question and the question was posed to us in a worded statement, we should also provide a worded solution to this question. So our response would be the diver hits the water at, you could say t equals, or you could spell it out, time equals to 2 seconds. Make your English professors proud. Capitalization and punctuation do count for something still in this day and age. So we know when the diver hits the ground. The second question says, well, what is the diver's velocity at impact? And if we're talking about velocity, we know that that's going to be the derivative of the position function. So we need to differentiate s of t. If I simply recopy it back, if s of t was equal to negative 16t squared plus 16t plus 32, so that's our position function. We know how to take the derivative of a polynomial by now. This will give us negative 32t, derivative of 16t is 16, and then the derivative of that constant 32 would be 0. So this gives us the velocity, not the velocity prime. So the velocity function is negative 32t plus 16. So if we want the velocity when it hits the ground, that's the velocity at 2 seconds. This is going to be negative 32 times 2 plus 16, which is negative 64 plus 16, which would be negative 48 feet per second. And again, if you think about this velocity as a vector, the negative symbol makes total sense because the diver is actually falling. They're moving towards the ground from the diving board. So the direction of their motion is downward, and that's why we see the negative sign associated with the velocity. Okay. So again, worded problem should give us a worded solution. The velocity, I'm just going to be brief about it. The velocity at impact is negative 48 feet per second.